So, uh, welcome everyone. Welcome to yet another video abstract algebra. Let's get more into the group. Okay. Let's write down some schema. So let's look at the first one. Let order of A be equal to n. Right. Then multiplication in the group generated by A is done in the same way. Is done in the same way done in the same way as addition in Zn, right? That is, if I want to add a raised to I mean, if I want to multiply a raised to I into a raised to j, this would be nothing but I plus j, right? Isn't it? That can be written as k, where k is congruent to I plus j mod n, or in other words, what I can say is I plus j is congruent to k mod n. That is the remainder which is left when you divide I plus j by, right? Similarly, if order of A is infinite, then multiplication multiplication in A is done in the same way as addition in Z, right? Isn't it? Right? Therefore, what happens is therefore Z and Zn are prototype, right, for all cyclic groups of infinite and finite order, right? So Z and Z becomes prototype for all cyclic groups. But, uh, let's look at more into this. Let's look at the theorem. Theorem. What we have is that A be an element of order n in group G, some binary operation, and let K be a positive integer, then subgroup generated by K same as subgroup generated by GCD of K and N. Right, that's one thing. And order of A raised to K would be same as N upon GCD of N. Right? Quickly prove this. Proof. Let's divide this screen into two halves. Use some line. Divide this into two halves. Proof is as follows. I don't have to scroll the screen again. What I want to show is if I go back, if I take it back to what I want to try. What we have is I will show that K and A raised to K and the GCD of K and N would have the same order and would be giving in the same group. Let's look at that. So with some different time. The first part, let D be equal to GCD of K and N. This would imply that D would divide K as well as E would divide. Uh, what I want to show is to show that the subgroup generated by A is same as the subgroup generated by D. Well, that's what we want to do. So let's look at this one. Uh, since D divides K, this would imply that there exists some R in Z such that K is nothing but R times, right? Therefore, what happens to K, A raised to K is nothing but it's A raised to R times D, which is nothing but A raised to D times, right? Isn't it? So what happens is, now we need to remember one thing first, that if I go back, okay, if I go back, what would you mean by subgroup generated by A raised to K, right? This would be set of all A raised to K power some n or some alpha, right? Where alpha belongs to Z. So it's set of all powers of A raised to K, right? So if we come back, same argument, okay. If we come back, then since A raised to K is some power of A raised to D, right? Therefore what happens is this would imply that A raised to K would be contained inside A raised to D. And since this is a subgroup, right? We know that every element generates a subgroup. Therefore, if this element is here, its all its power would be here. So this would imply that the set generated by A raised to K would be a subset of A raised to K. Right? Let's name this as one. Similarly, similarly, uh, since D is GCD of K and N, this implies there would exist what I can say PQ in Z such that D is equal to Pn plus Qk. Therefore, A raised to D would be nothing but A raised to Pn plus Q times K. This would be A raised to N raised to P if I use indices into A raised to Qk. This would imply that since A has order n, therefore this would be identity, and this would be nothing but A raised to K times K raised to Q. Therefore, what happens is A raised to D is nothing but A raised to K, some power of. This would imply that A raised to D belongs to subgroup generated by A raised to K. This would further imply that since this is a subgroup, the subgroup generated by A raised to D would be contained inside A raised to K. The reason being is A raised to K is closed. Right? If this is there, all its power would be there, right? So in particular, if A raised to D is there, its powers will also be there. So this is 2. So from 1 and 2, what we get is A raised to K is same as A raised to K. Is nothing but A raised to GCD of K, right? That's the first part. Let's look at the second part. How do we go about second part? Second part is also kind of, can also do that in a similar line. So let's kind of align to this. That continue next part. Send this line down further. Next, to show that order of a raised to k is nothing but n divided by GCD of n. One thing we need to note that since subgroup generated by a raised to k is same as subgroup generated by a raised to t, this would imply that order of a raised to k would be same as order of a raised to t, right? This is the very first fact we need to take care. Now, note that now let's see this. If I look at a raised to d up raised to n by d, this would be nothing but a raised to n because dd will cancel, and what this would be is equal to identity because as since order of a is equal to, right? Therefore, by the previous corollary which we have seen, we can note that order of a raised to d, whatever it is, would be less than or at the most equal to n by. Further, let I belong to n such that I is strictly less than n by d. This would imply that I times d, right, would be strictly less than n, right? This is fine. Now, therefore, let's look at n by d as an integer. Remember that. Well, okay. So therefore, what happens is a raised to id, right? A raised to d raised to I rather would be nothing but a raised to I times d, and this can never be identity as I times d is strictly less than n and order of a is n. So a raised to something which is strictly less than n cannot be identity because otherwise it will be a contradiction to the fact that order of a is n. Therefore, what we get is a raised to d raised to n by d is identity, and a raised to d raised to I is not equal to identity for all I less than n by d. Right? This would imply that order of a raised to d would have to be n by d. But from here we know that order of d is same as order of k. Therefore, order of a raised to k is same as n by d, which is nothing but n by GCD of n. That's what we have to prove in the first. I hope the proof is. Let's see this example here. Uh, let's see this example. Okay, this example. Uh, Suppose order of A. Let me take it to be. Um, uh, let's take 32. Uh, okay. Then what happens is this will generate a group of order 32, right? It will be a squared, and so on up till a raised to 29, a raised to 30, and a raised to 31. Group of order 32. Then find subgroups. Let's start with A, right? Since A generates, A is the entire G, but what else are the generators? Okay, remember that the result says that A raised to K and GCD of A raised to N comma K, right? Generate the same group, right? So, so the elements whose GCD with N is 1, all K's whose GCD K is, of course, K is between uh, K is between 0 and 31, of course. So any K between 31 and 0 whose GCD is 1 with 31 will generate the same subgroup, right? So if I look at what are the elements? Uh, 3, right? A cube has the same GCD as right. We look at GCD of 3 and 32. It's 1 because 32 is 2 raised to 5, right? So that's correct. Then a raised to uh, anything which doesn't have a 2 as a factor, right? Uh, a raised to 4 won't be a raised to 5, yes. A raised to 6, no. A raised to 7, yes. A raised to 8, no. A raised to 9, yes. A raised to 10, A raised to 11, yes. A raised to 13, yes. This is same as A raised to uh, 14, 15, yes. Same as A raised to 17. This is same as A raised to 19. This is same as A raised to 21. This is same as A raised to 23. Same as A raised to 25. Same as A raised to 27. Same as A raised to 29. A raised to 29. Same as A raised to 31, right? One can check what would be the order of 3 uh, in this group, right? It would be exactly yeah, right? And this all will have the same order as uh, order of 3, right? So this would generate. These are the generators of um, this group, right? Uh, all right. Uh, Now let's look at what are the other subgroups. So these are all equal. What about a square? Okay. Uh, all those elements whose GCD with with 32 is 2 would be here. So a square is there, right? Next one would be a4 with 4 with 32 is not 2, right? It's 4. 6 with 32, yes, right? Then 7, no, 8 with 32 is 8, and 10 with 32, yes. A power 10, then a power 12 with 32 is 4, right? Yes. So that won't be there. Then 14, yes. Then 16, yeah. 16 with 32 is not 2. 18, yes. Right? That's same as 8 is to 20, yes. 20, no, 4, no, 22, yes. 22, yes. Then a raised to 24, no. 26, yes. And this is same as a raised to 28, no. 30, yes. Right. So these are all the um, subgroup generated by 2, and these are all equal, right? Then let's look at what is subgroup generated by 4. What are the elements which are divisible by whose GCD is 4 with n. If I look at this is A4 is done, right? Then A8 with with 32 is no, that's 8, right? A 10 is done. A 12, yes. Yeah. Then what else? Um, 32 is done. A 12 is done. 14 is done. A 15, 16, A 16, A 16. Uh, no. 18, 18, 18, 18. No. 20. Yes. Right. Then 24, yes. Same as no, 24 would be uh, yes, yes. No, this will be 8. No, 24 won't be here. 28 it should be, right? And that's it. That's it. That's all we have in this, right? And what is left is A8. A8 would be let's see. Okay. A8 would be A would A8 would be same as 14, 15, 16, 16, 18, 24, right? 24. That's it. And then next one is A16, right? A16 would be A16. The last one would be A32. Identity, right? So if I list the subgroups, let's look at these subgroups on the extreme left. So what I have is A, that's uh, that's entire G, and order of A is 32, A raised to 1. Remember this. Then A square, right? That generates a subgroup of order. Um, is this? What is this? Its order would be exactly half, right? The order of A squared would be 32 by GCD of 2 and 32. That's 2, right? That comes out to be exactly 16. Then A power 4 would be, order of A power 4 would be GCD of 32 and 4. That's 4. So what will be the elements? 8, right? Then A raised to 8 would have uh, order order of this 8 is how much is exactly 4, right? Then we have A power 16. This will have A power 16 as order 2. The last one is A power 32, which is exactly having A power 32 will have exactly one element, right? So you can see the pattern kind of. First of all, if I look at this case, they are all divisors of 32, right? These all are divisors of 32. Do you see this? And if I look at their orders, right, they are also divisors of 32, right? This is one fact I would want you to know, right? So how many subgroups? I will have a unique, right, for every subgroup. So let's look at that note here. Note, note that for every divisor P of n, there exists a unique subgroup of order n by d. For every divisor I have, so look at the divisors here. Divisors were 1, 2, 4, 8, 16, and 32, right? So corresponding to 1, I have a subgroup of order 32. That's the entire group, right? Then corresponding to 2, I have a subgroup of order. That's a unique subgroup, by the way. All are any other subgroup order to this, it's equal, right? I mean order 16. That's then 4, its order is 8. Corresponding to 8, I have a subgroup of order 4. Corresponding to 16, I have a subgroup of order 2. And corresponding to 32, I have a subgroup of order 5, right? That's the idea we want to put forward here. So that's the very first observation you can make, right? We'll have more properties here, but I hope up till here everyone what exactly we are trying to, what exactly what is the direction we are moving towards. Now, with this theorem, there's this immediate corollary which follows. Quickly, let's finish up that line here so that just, just divide this half. Let's just divide this part into two halves. So let's look at that. Corollary is for the what it says is finite group, that's obvious, right? Finite group order of an element divides order of the group. Okay, uh, let's look at this one. Let proof of this finite cyclic group rather. Let me add a finite cyclic group. Order of an element divides order of a group. That's very much um, trivial. Uh, well, it is nothing to prove actually, but then let's look at this. Let G be a finite cyclic group. Finite cyclic group generated by A. That is, let G be equal to A, which is set of all A raised to n in Z, right? So let X belong to G. It would imply that X is nothing but some power of A raised to K for some K in Z, right? So therefore, okay. So let me take an element x in G. Therefore, since it's generated by A, it must be some power of K, right? Uh, let D be equal to GCD of K and N. Then we know that order of A raised to K is nothing but N over, right? This is what uh, this is what we know. Also, what we know is also if I look at um, N can be written as N over D times D. Let me name this as star. Therefore, from star we conclude that uh, N over D divides N. Simplifies, but N over D is nothing but order of A raised to K. Therefore, and this implies order of but this is nothing but X. Order of X divides N for every X. Right? Let's look at further into more corollaries of this theorem. Do the same part. Shapes, let's go to shapes and then just divide this. Okay, so let's look at the next corollary. Sorry, let me use some different pen. It's easy. So, corollary two, sorry, of the same theorem, of course. What it says is, if suppose I have a, so let order of A be equal to N, Okay, then a raised to I would generate the same group as a raised to j, right? If and only if the if and only if GCD of I with n is same as GCD of j with n, right? The same ideas, right? And order of a raised to I is same as order of a raised to j, if and only if GCD of n over I is same as GCD of j over n or n over j, doesn't really matter. Well, the same part, same kind of ideas, put it in a different context, but the thing is same. So let's try to prove this. Proof. Okay. So let me use this I notion here. Let D1 be equal to GCD of n and I, and D2 be GCD of j and n. You can also prove this. So by previous theorem, what I know is order of a raised to I is same as d1, and order of a raised to j is same as a raised to, right? Claim, what I have to prove is uh, if I use this notion, um, what I want to prove is that uh, a raised to d1, right, uh, is equal to a raised to d2 if and only if this thing boils down to proving that a raised to d1 is same as a raised to d2 if and only if d1 is equal to d2. One way it is simple. Uh, if 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 d1 is equal to d2, right, then this would imply that a raised to d1 would be same as a raised to d2. This would imply that a raised to d1 same as a raised to d2, and the matter is over, right? So this is like the other way. Let's look at the direct part. Direct part would be we would have to do some work. Let's look at this one. So suppose order of, I mean, the subgroup generated by a raised to d1, say suppose it is same as subgroup generated by a raised to d2, right? Then this would imply that so my claim is d1 is equal to d2. Well, this would imply that from the top, order of a raised to d1, right, would be same as uh, yeah, order of a raised to d1 is same as, because they generate the subgroup generated are equal, therefore the order of the elements should also be equal, right? But this would imply that I know that this is by the previous theorem is nothing but n over d1, right? And this is same as n over d2, right? By corollary. Uh, yeah, it's by previous theorem, not corollary. By previous theorem. You know what theorem I'm referring to. I hope, I hope you know I'm referring to. By previous theorem. Okay, the previous theorem which we have just proved. Uh, Therefore, if n by d1 must be equal to n by d2, then it better be d1 be equal to d2. Right? Hence, the hence the first part. So the first part is done. The proof is yet to be. It's far from over, right? The proof is far from over. Let's look at the further part. Okay. What we need to prove is a raised to I. The order of a raised to I is same as Uh, so, so from here, what we can conclude is therefore, subgroup generated by A raised to GCD of I comma n is same as a subgroup generated by a raised to GCD of j comma n if and only if GCD are equal. GCD of I and n is same as GCD of j and n, right? So the first part is over. Second part, let us see how do we proceed. Now the next part, to prove next part, what I have to claim is lines for our reference. A line for our reference so that we can divide this exactly into two halves. So let's use a pen. The next part we would have to show is next. I'm using the same notations. Next, to show that what we have to show is in the next part that a raised to I, the order of a raised to I is same as order of a raised to j, if and only if d1 is equal to d2, right? This is what um, we'll have to show. Uh, all right, let's look at this one. Note that order of a raised to I is nothing but n over d1, and order of a raised to j is nothing but n over d2, right? So therefore, if d1 is equal to d2, if these two are equal, then this would imply that I'm just using the notation. This would imply that order of a raised to I would be nothing but n over d1, which is same as n over d2, which is same as order of a raised to j. Therefore, a raised to I becomes equal to order of a raised to j. On the other hand, right? On the other hand, suppose a raised to I is equal to a raised to j. What I'll have to show is d1 is equal to d2, right? But this is uh, this is pretty much easy, because what happens to order of a raised to I is this is same as order of subgroup generated by a raised to I, which is same as order of subgroup generated by d1, right? And and um, and this has order what? This has order n by d1, right? And what happens to order of a raised to j? Order of a raised to j is same as order of subgroup generated by a raised to j. That is same as subgroup generate order of subgroup generated by a raised to d2. This is j. I hope you can make out j, right? This is same as this. And what is the order of this? This is n by d2, right? Well, therefore, what happens is if this and this are equal, so therefore, if order of AI is equal to order of AJ, then this would imply that these two must be equal. Therefore, n by d2 must be equal to n by d1. And in this case, what happens is d1 must be equal to answer. That's what we have to prove. Answer. We assume this, we prove this, we assume this, we prove this. So I hope we can put in the notations. I've just used the notations, but you can just that's the notations I've used. You can put wherever D1. You know what I've just fixed the notations in the main part, so you can look at those things one more time. Well, the next part of this, right? So here's the next corollary for the same theorem. Let's write this as corollary 3. Okay. Uh, let order of A be equal to n. I'll sometimes use O of A. Uh, then the generator, the group would be generated by some area if and only what I was talking about today in the class, right? That uh, uh, GCD of J and N and order of A is same as order of A raised to J if and only if same idea. J and N. Okay, so A raised to J will generate the same subgroup as A, provided they have GCDs. I mean, relatively prime GCDs. Okay, so this is kind of very much easy from previous theorem. What we're gonna use is previous theorem. So from previous corollary, that is corollary 2. I don't write this in exam, if at all. This these things you need to prove. I'm just doing because I have already proved that. But if you're proving this result, I hope you better prove it. Uh, but I can just use this. Generally, see people giving me from previous theorems those things which doesn't make sense at all. You either state a result or something like that. You can do to, up to the question which is asked. Um, uh, from previous corollary, we know that what do we know? That A raised to I is equal to A raised to J. The subgroup generated by A raised to I same as A raised to J. If and only if the GCD is with uh, same as GCD of n J, right? So substituting I is equal to 1 in 1, we get, right? If I put I equal to 1, what will happen is this will be A, right? A raised to J. If and only if GCD of n with 1 is same as GCD of J with n. But GCD of n and 1 for any n is 1. So this would be A subgroup generated by A is same as subgroup generated by J if and only if GCD of n with J is 1. That finishes the first part, right? For the second part, we do the same thing. Also, um, we know that we know that um, order of A raised to I is same as order of A raised to J. If and only if GCD of I with n is same as GCD of J with n. Do the same thing. Um, therefore, taking I equal to 1, we name this as 2. In 2, what we get is we get uh, A raised to 1 would be equal to A raised to J if and only if, right? GCD of J with n is GCD of 1 with n. That is, order of A is same as order of J if and only if GCD of J and n, right, is, remember this. Okay, so uh, that's what we have in this corollary. Right? We would take some examples and check out what exactly we mean, right? Uh, this, uh, this kind of thing. Uh, so let's look at, look at what are the generators of Saturn. Uh, as I said, as I was saying when I was doing actually the look at um, let's look at this theorem. Um, theorem here. Um, an integer, an integer, an integer k in Z uh, is generator of Zn, right? If and only if GCD of k with n. The proof is just like from it's based on the previous result. Note that I know one of the generators. Note that one generates Zn. This would imply that order of one would be equal to let k be generator any generator of Zn. Therefore, previous theorem, by previous theorem, uh, this is same, right? This is same if and only if GCD of 1 and n is same as GCD of k and n. This would imply that 1 is k if and only if GCD of k by n. So whatever we have done so far, let's kind of put them in some problems before we actually proceed to do the very most important theorem in the cyclic groups. Okay, as a fundamental theorem of cyclic groups that can be done later, right? Later, maybe whenever we are actually doing. But I think the things would get lengthier. Uh, Problems, example. Let me consider, say, Z Z12. Or why would Z I consider so small number? Let me consider Z25. Let me go to Z. Oh man, Z25. So what do I have is 0, 1, and so on up till 24 bar. Right? I know that 1 generates this. So what I know is, one thing, that 1 bar would always give me 25. Okay. I want to check out what are the other numbers which would always generate Z25. By the previous theorem, uh, what happens is all the generators must have GCD with with n to be equal to 1, right? So what are the numbers? So this would be same as what are the numbers whose GCD with 25 is 1. Let's list out all the generators. That's 2, all odd numbers, right? 3, 6 also, right? 6 doesn't have anything common. 25, right? Uh, then all, or you can just look at the 7, then 8, and 9, and so on and so forth. All will give you all will have order 25. Okay, that can be checked out. Yeah, right. The second example which we can take is of let me go a bit further and go to U30. Okay, it would be very nice to go to this, but let's go a bit because I want to also do. I can leave U50 to you. I can just because you have more time for things, which are a bit lengthy. So I leave U50, U50. Find the generators, find all the subgroups of U50. I'll leave this as an exercise for you. Okay, you can do. Um, what I want to do is I want to do something else. So let me go to that. I'll do something a bit, something which is a bit small. Example. Let me take well, nice example, which kind of give me plenty of small also, of course. Let's go to right. So what is happening is I have one, I have five, then I have seven, then I have uh, then 11, then 13, 15. No, not 15, not 15, not 15. Sorry, 16. No, 17. And that's it. Yeah, that's fine. I want to look at what are the generators of so U18 has order of U18 is so first of all, if I get one generator, I can identify what are the all generators of this. So to find one generator, I will have to dirty my hand. Uh, well, let's look at this one. What happens to 5? 5 raised to 1 is 5. 5 square would be 25. 18, if I go, I get 7. Then 5 cube is 35. This would be 17. 5 power 4 would be, so order of 5 would be 6. Can directly make out that because order has to be dividing 6, which is not the case. So 5 power 4 would be 17 into if I look at 5 power 5, it would be 17 into 5, right? What does that give me? 17 into 5. 17 into 5 would give me 85 if I'm not wrong. Uh, if I go modulo 18, um, so this would be 13 if I'm not wrong, right? Then 5 power 5 obviously has to give me the element which is not here. That's 11. And 5 power 6 will give me 1. You can check 5 power 5. What is 5 power 5 by this? 13 into 5 would give me 65. And if I go modulo 18, uh, give me yeah. So order of 5 is 6. So 5 generates U18. Now I want to check what are the elements which would generate U18, right? So this means 5 raised to 1 is also equal to some 5 raised to k, right? If and only if GCD of k and 6 is 1, right? This means what are the elements for what are the values of k first of all, right? K can be 1, which is already there, right? K can be k can't be 2, k can be 3, k can't be 4, k can be 5. Right? So I have two generators of this, and what is the generator? This will be 5 raised to 5, which is 11, right? From here I can just find out all the generators. Just take one which generates, and you can just look at